Okay, so we're continuing with chapter 7 here, so we spent some time looking at qualitative changes in equilibrium systems, right? So looking at things like temperature change and concentration and the shifts that kind of happen in equilibrium systems. So either shifting towards the product side by having the forward reaction increase in the rate, or looking at the shift to the left or to the reactant side where you have the reverse reaction that is increasing in rate. So today we're going to be looking at quantitative changes. So not necessarily looking at shifting left or right, but actually looking, not only saying the shift, but actually calculating the changes that happen to those concentrations. And there's actually quite a few different kind of scenarios you're going to come across when you're dealing with quantitative work here. So I've kind of outlined 3 of the main ones that you will see. So we can use quantitative calculations to determine if you have a system that's at equilibrium. So maybe we don't have information about the rates, and we don't have information about, we don't have a graph or any sort of data to go by. But if you have concentrations at a moment in time, you can actually calculate to determine whether or not the system is in equilibrium. So we'll look at that one there. The second scenario is essentially anticipating. So let's say it's not in equilibrium. So we do our calculations from the first 2 actually kind of go hand in hand. So we do our calculations for the first one and say, okay, well, it's not at equilibrium. We can actually predict what shift will have to take place in order for that system to reach equilibrium. So essentially, you're going to be looking at this value and comparing to what it should be if it were in equilibrium, and then indicating what changes might have to occur. And then the last one that we're going to look at in this section anyways, there are plenty more to look at ahead, but the equilibrium concentrations of reactants and products when given the initial conditions and the K value. So what this one here is indicating is basically we can use the ICE table and the K value for a specific equilibrium to discuss quantitative changes that happen in equilibrium systems. We're looking at, values that change over time, right? So, and we've actually already been doing ICE tables kind of all along here. Especially when you were doing K calculations and setting up your K expressions. But this is going to be a little bit of a more advanced approach. So if you remember at the beginning of this chapter, I did mention that this is going to be a building section. It's really important that you know how to set up this table. It's because we're now going to kind of bring it to the next level here. So let's start taking a look. So we're going to discuss the first 2. Remember I mentioned they kind of go together first. So let's say we have, you have a scenario where you may or may not have an equilibrium. So equilibrium constants, so remember your K value, technically your K value can only have equilibrium concentrations within it. So if you remember when you're setting up your K, right, so you have your products over your reactants, the concentrations that you plug in here have to be concentrations at equilibrium, right? So you can't put initial or something that's in between initial and your equilibrium. If you're indicating that something is a K value or a K expression, they must be equilibrium. It's assumed, okay? Now, part of this whole question that we're talking about here is, well, what if we don't know if the system is at an equilibrium yet? We're not sure. Well, you can't really call it a K expression technically, because K expressions are equilibrium. But what if we don't know if this is equilibrium? What essentially we're going to do is we're going to calculate something called a Q, which is a reaction quotient. So essentially what that means is it's the exact same expression as K, okay? The same expression as your K, except you can actually, I know that the note here says you can put initial concentrations in there, but you can actually put any concentrations in your Q expression. So your Q is literally going to be the same setup, right? So products over reactants, except the concentrations that we can plug into this do not necessarily have to be at equilibrium. It might be, at the beginning of the reaction, the initial concentration. It might be, 2 minutes into the reaction. It could be 15, 20 hours into the reaction. But the Q value is where you basically do not know if it's equilibrium or not. Sometimes we refer to this as being like a trial K. So it's like we're going to plug some numbers in here. We don't know if it's equilibrium or not, but we're going to set up the same as the K expression and see what we have. Okay, now why is this important, or what does this tell us? Well, depending on the value you get for your Q, when you compare it to your K value, you can basically predict what is happening within your system. So if you recall, we talked about the size of K. So if we have a very large K, that means that we have a lot more product in comparison to reactants, right? So the numerators are larger value. If you have a small value of K, that means typically you have more reactant, right? A larger denominator. But whatever the K value is, that is a constant for that reaction at that particular temperature. So let's say we have a reaction where, let me change the color. So let's say a specific reaction at a certain temperature, the K value is 20, right? So we get a value of 20. Well, let's say we plug in some numbers into a trial K or RQ. If you end up with the value of 20, that indicates, oh, we do have equilibrium because the Q is equal to the K, right? But if you have a value that's off from K, right? So let's say I have a Q of 10. That tells me this is not at equilibrium because equilibrium would have to be equal to whatever the K value is. So by looking at this number and comparing it to the K, we can basically start to say, okay, well, does this reaction need to make more product or more reactant to get to equilibrium, right? So if your Q value is smaller than K, that means that there's not enough product that's there. So we have to increase the value. So if I have something that's a Q of 10 and it should be a 20 at equilibrium, I know more product will have to be produced, so the forward rate will have to increase. If your Q value is much larger than K, that means there's too much product, it would have to shift to the left to alleviate that. And that's exactly what's indicated here. Right? So when you determine the chemical system is at equilibrium or not, we can start to also predict the shift that's necessary for it to be that. So again, to recap, if Q is equal to your K, that means you are in an equilibrium situation. If your Q is larger than K, that means there's too many products. It's going to have to take a shift left to make more reactant, right? Get that denominator value up. And if Q is less than K, that means that you don't have enough product there. We have to increase the value, which means it's going to have to shift to the right. Okay, so again, when do you use this Q setup? It's basically when you're not sure if an equilibrium is happening, and the question will literally ask you, is the following system at equilibrium? Okay, well, the only way to really know that is to calculate out your Q and compare it to your K. So let's take a look at an example. I'm going to do A with you, and then I'm going to ask you to pause the video and try B out on your own. All right. Okay, so let's take a look at what we have here. So the following reaction occurs in this should be container, a closed container at 445 degrees Celsius. The equilibrium constant is 0.020. So that means at this temperature right here is our K value. We have our balanced chemical equation, which is nice. We don't have to write that out. And it's asking, is the system at equilibrium in each of the following cases? If it's not at equilibrium, predict the direction in which the reaction will need to proceed to reach equilibrium. So notice we're given concentrations for each of our components here, right? Our reactants and our products. But notice it's not telling us, is it equilibrium? Is it initial? That's the whole point. We don't know what it is. So the first thing we're going to do is we're going to set up our Q expression here, right? We cannot call this K because we don't know if this is equilibrium concentrations or not. So we have our products. Our products over our reactants. And remember that the exponents are the coefficients in front. And essentially, we're just going to plug in the numbers that are here, right? So we have our hydrogen, our iodine, and our HI, right? So let's do that. Right, so we have 0.04, and then 0.01 over 0.14 squared. Okay, so when you calculate this out, we get a value of 0.02. So in this case, you're going to compare this to the K. So Q is actually equal to K in this situation, 0.02, 0.02. So that means this is at equilibrium. So we don't have to, indicate the shift because it already happens to be. So these, part A, those concentrations are equilibrium concentrations. Okay, so pause the video here and try out B. Okay, so obviously you can see the concentrations are different. So it's safe to say that it's not going to be at equilibrium. Okay, but calculate Q to prove that and then indicate this shift. Okay, so hopefully you've tried that out. Let's see how you did. So the Q expression is the same because it's the same, chemical reaction. And we plug in our values, and you should have received a value of 0.34. So in this case, 0.34 is way larger than 0.02. So in this case, we have a situation where it's definitely not at equilibrium, and there is way more product than there should be, right? So the value is way bigger. So we essentially have to lower the denominator's value. So we'd have to lower the numerator's value, to lower this value overall, right? So you have a smaller value over, a larger value over a smaller one. So in this case, we would have to shift towards the reactant side to the left to make more reactant in comparison to the product, right? So this is the first, if we go back to what we were first saying about the types of scenarios you're going to see, this essentially checks off those first two. So saying if a system's at equilibrium, and if it's not, you compare your Q to your K to indicate the shift. Okay, so let's look at another example. So this is where we're going to be dealing with our ICE table examples with dealing with K and quantitative calculations here. So let's look to see what we're dealing with. So at a particular temperature, we have the KQ for a reaction, and the K is 400. And we're dealing with the same reaction, but we don't know the temperature, so K is different, right? So technically, you can have the same reaction over and over and over again. Your K value will be different at every temperature, right? So it's saying if the initial concentrations of hydrogen and iodine gas are both 0.04 moles per liter, okay, so we have the initial, that's key. What is the equilibrium concentration of hydrogen? Okay, so the difference between this question and the ICE tables you have done up till now is I want you to recognize they did not give us any information about equilibrium concentrations. So normally you're told at least one thing, reactant or product, but you're told one concentration that's at equilibrium. So here's a situation now where we're going to have to change our approach to this because we don't have any values. Okay, but the ICE table setup is going to be exactly the same.